wanted to work through an example that involves the magnetic field equation, which is the relationship between magnetic field and magnetic force for a moving charged particle in a magnetic field and experiencing a magnetic force. And also involves circular motion, which is a classic type of motion for moving charged particles in magnetic fields. So in this problem, we're asked to imagine the Earth. The Earth is surrounded by a magnetic field, and we have a proton, a charged particle, that's orbiting the Earth in a circular path in the Earth's magnetic field. And we're told it's orbiting at the Earth's magnetic equator, where the magnetic field has a strength of 4 × 10⁻⁸ Teslas, so a very small magnetic field. And that magnetic field is perpendicular to the circular motion of the orbiting proton. And finally, that proton is orbiting at an elevation, a height above the ground, of 1,000 kilometers. So from all that information, we're asked to figure out the speed at which the proton orbits the Earth in the magnetic field, and also the period that the proton takes to orbit to complete one orbit of the Earth. This is a problem in which the proton is experiencing a magnetic force, and that magnetic force is providing a centrifugal force, which causes the circular orbiting motion. So I'm going to start this problem by sketching out the magnetic field, sketching out the circular orbit, and annotating the sketch with the information I know, which is things like the magnetic field, which is things like the radius of the circle of the orbiting proton. And then we'll go on to address the questions of the velocity and period. Okay, so here's my sketch of the problem. In green, these equally spaced circles are meant to indicate a uniform magnetic field that's emerging from the screen, from the overhead. And that's the magnetic field at the equator that the particle, the proton, is moving in. In red is the circular orbit of the proton. And here in black, I've indicated the radius of the circular orbit. It's 1,000 kilometer elevation, but we've got to add that to the 6,000, almost 400 kilometer radius of the Earth to actually get the radius of the orbit. So the radius of the orbit is about 6.4 times 7.4 times 10 to the 3 kilometers, or 7.4 times 10 to the 6 meters. I've also added in magenta here the proton. I know its charge, I looked it up, 1.6 times 10 to the -19 coulombs. I know its mass, looked it up, 1.67 times 10 to the -27 kilograms. And here's the unknown velocity. We want to figure that out. We also want the unknown period of the orbit. I'll call that uppercase T. You want to figure that out. The basic idea here, the key idea, is that this proton is undergoing circular motion in this magnetic field. That is that the magnetic force that's conveyed by the magnetic field is providing the centrifugal force that causes the circular motion. And so I'm going to write down that key starting point over here on the right-hand side. It's this statement. This is a statement about strengths of the centrifugal force and the magnetic force. It's a statement that the size, magnitude of the centrifugal force equals the size and magnitude of the magnetic force in this situation. We can check the directions. I'll discuss the directions at the end of the problem. Anyway, that's our master equation. That's our key concept, a key idea. I'm going to fill in my understanding of centrifugal force and my understanding of magnetic force to derive an equation for the velocity and ultimately the period of the orbiting proton. So the centrifugal force, you might remember, is dependent on the velocity of the motion in a circular path, the radius of the motion in the circular path, and the mass of the particle that's orbiting in the circular path. It's mv squared over r. And it must be that force, that necessary force for the circular motion, is provided by the magnetic force that's acting on the particle. And the magnetic force that's acting on the particle is the product of the charge of the particle, the speed of the particle, the magnetic field that the particle is immersed in, and the sine of the angle between the magnetic field direction, which is out of the screen, and the circular motion, which is in the plane of the screen. So that's actually sine of 90 degrees. So this is our starting equation, having filled in how centrifugal forces work, how magnetic forces work, and we've just got to rearrange it now for the velocity of the moving proton. So we can do that if we simplify it. We could replace the sine theta by 1. We've got a v squared on the left, a v on the right, so we can cancel ab. And then all we've got to do to isolate the velocity of the proton is multiply through by r, divide through by m. And if we do that, we get q b divided by n. So that's our equation for the velocity. If you think about this equation, it has two distinct parts in it, really. It has one part, the q over m part, that is a characteristic of the charged particle that's moving in the circuit. So it depends on the charge of the charged particle, it depends on the mass of the charged particle. It has nothing to do with, the particular circle it's moving in. It has nothing to do with the magnetic field it's moving in. It's all intrinsic properties of the particle. So we can fill those quantities in. I'm just working the size, the speed, not the direction, not the sense. So I'm just going to put in always sizes, magnitudes for the values. So 1.6 times 10 to the minus 19 coulombs is the charge. 1.67 times 10 to the minus 27 kilograms is the mass. And then this multiplies the radius of the circular motion that we said was 7.38 times 10 to the 6 meters, multiplied by the field, and that field was 4 times 10 to the minus 8 Teslas. And I've already multiplied all these numbers together to get the velocity. I got 2.8. 2.8 times 10 to the 7 meters per second. So it's traveling at a very high speed in order to create a magnetic force that can provide the centrifugal force. It's 2.8 times 10 to the 7 meters per second. That's actually about 10% of the speed of light. We also wanted to calculate the period. This is the time to complete one orbit, uppercase T. We can calculate that just by using the relationship between the velocity you're moving at, the distance you're traveling for, and the time that it takes. So velocity equals distance over elapsed time, or we can turn that right around to make the elapsed time, the period in this case, is the distance, 2 pi r's, the circumference of the circle, divided by the velocity which the proton is traveling at. Clearly, right, if the circle was a larger circumference, it would take longer time. If the particle was moving faster, v was larger, it would take less time. So it makes sense in that regard. We just got to fill in the numbers here, because we know in the numerator we've got 2 pi times the radius, which again is this 7.38 times 10 to the 6 meters. And then we've got to divide that by the speed that the proton is moving at. That's the 2.83 times 10 to the 7 meters per second. And if we divide one by the other, we get a rather everyday number. I got 1.6 seconds. It's 1.6 seconds. That's 1.6 seconds to go around the entire Earth at 1,000 kilometers above the Earth's surface. So it takes a very high speed, 10% of the speed of light, to completely orbit the Earth in 1.6 seconds. And so that's the solution to my problem. Let me just comment on the direction of the magnetic force and the sense of the circular motion. So if we look at the sketch here, the particle, the moment I've drawn it here, is basically on the bottom portion of the circular orbit. It's mostly moving over towards the left. So I could point the palm of my right hand towards the left. And if I do that, and then I curl my fingers out of the screen, that's the direction of the magnetic field. My thumb will point in the direction of the magnetic force. So if I do that, I'm pointing the palm of my hand towards the left. I'm curling my fingers upwards out of the screen. My thumb is indicating that the magnetic force, FB, is towards the center of the circle. So it is indeed acting as a centrifugal force, holding the particle in a circular path. Anyway, that's an example of, firstly, the magnetic field equation, which is a more complicated field equation than the electric field equation or the gravitational field equation. It's also an example of circular motion in uniform magnetic fields, which is a very important class of motion in magnetic fields.